Hello, I'm Channa Bankapur. I'm going to discuss my solution to the LeetCode problem clone graph. It's today's problem in October LeetCoding challenge. So the problem definition is as follows. So we need to create a deep copy of a graph, which is called cloning of a graph. What does deep copy or clone means is all the nodes in the graph needs to be independent in the sense that they should not point to any node in the source graph, right? They should point to the corresponding nodes in the clone graph. That's what deep copy means. And the graph is connected and then undirected. And look at the representation of the graph. Every node has a field called value or val, and then a list of neighbors, essentially pointers to neighbors. Suppose there is a node called 8 here and a node 3. So if there is an edge between 8 and 3, the representation demands 8 looks like a neighbor of 3 and 3 looks like a neighbor of 8, right? So a node is an edge is basically has presence in two different nodes, right? And so let's extend the example to a few more nodes. Suppose there is a node called 6 and there is an edge between say 8 and 6 here, and maybe there is an edge between 6 and 3 also, and another node 9, and 9 has edge between 6 and 9 here. So this is the graph and we want to clone this graph, right? So the method I'm going to use here is DFS traversal. So I'll traverse through the whole graph. By the way, actually we are given a pointer to one of the nodes in the graph. Suppose we have a pointer to node 8, and because it is connected, we should be able to reach to any node in the graph, right? That's why we should be able to, if I run a DFS traversal starting from node 8, I'm going to visit every node in the graph. So let's go through DFS traversal and then create. So when I'm going through DFS traversal, when I visit a node, I'm going to create a corresponding node in the clone graph for that. And assigning pointers is obviously the trickier part. We'll see how does it work. So I start DFS traversal on node 8. So the first thing I do is obviously I'm going to mark it as visited, and then immediately after that I'm going to create a node 8 here in the clone graph, right? So as soon as I create it, and then when I mark these neighbors, I should not be marking neighbors in the to the original graph, right? So that's why I should have some kind of mapping between a node in the source graph with a node in the cloned graph. So if I know somehow, if I give pointer to this node 8 in the source graph, if I can get the pointer to a node, the corresponding node in the clone graph, a lot of things are going to be easier. So I'm going to use this kind of mapping here, right? So this is mathematically more like a function, right? Function from source graph to the clone graph. It's a one-to-one mapping essentially, right? So now DFS is on 8, and then we already created the node. Let's go through its neighbors. 3 is a neighbor, 3 is not yet visited. So I'm going to call DFS on that. So I'm going to call DFS, and the first thing I'm going to do is create a new node for that in the clone graph. So as soon as I create, I'm going to have this kind of mapping, right? So, and then look at the neighbors of 3 now. So 8 is a neighbor of 3, but 8 is already visited. But now I need to somehow make this pointer happen, right? So 3 should point to 8 in the clone graph. 3 should not point to 8 in the source graph. So how do I do that? I look at 3 to 8 is there is an edge, there is a neighbor 8 from 3 in the source graph. Then I'm going to take the mapping of 3, which is 3 in the clone graph, and I'll make it, I'll add a neighbor to that, which is going to be pointed to mapping of its neighbor in the source graph, which is going to be 8. That's why this mapping is going to help us. And that's how we're going to have this pointer 3 pointing to 8 in the cloned graph, right? So that's the trickier part. And once I do that, I'm going to look at another neighbors called 6. So 6 is not yet visited. So I'm going to visit that. That means DFS 6 is called, and that's going to create this node. And a corresponding map is also updated. So now 6 is going to look at its neighbors. 8 is a neighbor which is already visited. So I'm going to just set this pointer. And 3 is also a neighbor which is visited. So I'm going to set this pointer, right? And what else? So there's one more node called 9. 9 is also a neighbor. So, but it is not yet visited. So I'm going to call DFS on that. So that is going to create a node. and create a mapping here, right? So now look at the neighbors of 9. So neighbors of 9, 6 is the only neighbor which is already visited. So I'm going to just mark this pointer, right? And 9 is done with this DFS traversal, so it's going to return back to 6. 6 earlier it visited 8 and 3, and it actually pointed to them there, but it didn't point to 9 back then because 9 was not even created then. It called DFS of 9. So now it knows that 9 is already created. Now it's going to point to 9. So 6 is going to point to 9. All right. Now 6 is again done with the DFS traversal. It's going to return back to 3. Now 3 earlier called 8 first and then 6, but 6 was not even created then, so we don't have a pointer to 6. So now we know that we have a pointer to that, or we have a node called 6. We are going to have a pointer to 6, right? So that's how DFS of 3 is also completed, and it's going to return back to 8. 8 earlier called DFS of 3. Now it's going to point to that, and it looks at another neighbor called 6. 6 is already visited now, so it is going to just make a point to that, right? So now DFS of even 8 is also completed. We need to just come out of the DFS. When we come out of that one, what is the answer? We already created the whole clone. So the answer is whatever the original node was, this 8 in the source graph. Now I should return pointer to the 8 in the destination graph or the clone graph, which is going to be our map of the original node. That's my answer, right? So this should work. It's a simple DFS traversal again, but yeah, we are using this mapping. That is the trickier part, right? Let's look at my code and see how does it work, right? So this diagram actually ensures what you need to do. If this is the original graph, returning the original graph is not obviously a way of copying it, and returning a cloned graph where all the nodes are cloned but some pointers are pointing to say original graph is also not acceptable. And this is what is acceptable, whatever we discussed, right? So let's look at the code here. See, it's not really complicated code. It's a simple DFS code. um, Now look at the method cloned graph. This is what we need to implement, and pointer to node is given. So if this is null, this is the base case. We don't have to create anything and return. Now I'm setting up this mapping. It is basically a pointer to node, mapping to another pointer to node. So which is empty in the beginning. I'm going to call DFS on this node. Obviously mapping is passed along. And look at this DFS of node. So as soon as I get here, I'm going to mark this one with the mapping here, so that I create a new node with the value of the node itself, and then map from node of the source graph to the clone graph. Right? This is mapping is created, and now I'm going through every node in the every neighbor of that node. So this is the list of neighbors. I'm going through every neighbor here. So how do I make sure whether it is visited or not is, if I see if the mapping for that node is not created, that means it is not yet visited. So that's why I'm looking at the count of neighbor in the mapping. So I'm using mapping as also basically a way of knowing whether a node is visited in my DFS traversal, right? So if it is not yet visited, I'm going to call DFS on that first, right, on the neighbor, right? So whether I call DFS on that or not, when I come back here, now I need to set the pointers. So this is the trickier part. Line number 34 is obviously the trickiest part. So look at this. We have node here, and I'm taking the mapping of that. That means the corresponding node in the cloned graph. And to the list of neighbors of that, I'm going to add a node which is the current neighbors mapping. So current neighbor is this, which is in the source graph, and map of that is going to be the corresponding node in the clone graph. So that I'm going to add it to the list of neighbors. So this is the trickier part. And yeah, so now I think everything is covered. So once you are done with that, you're going to come back and look at what we are returning. Node is the original node or the starting node of the graph. And mapping of that is going to be the corresponding node in the clone graph. I'm going to return that, right? So this does the whole job. Let's see whether it works. It should work. I have seen this working already. Yeah, looks good. Let me submit it. Right, it is accepted. All right. So you probably already know the BFS, sorry, DFS traversals analysis, and it's going to be similar to that. except that there is a map here. So I'm using unordered map essentially because this is like hashing, and all of these accesses, adding a pushing back, are basically creating something like this one, accessing something and adding a new value to that, is all going to be be constant time, expected constant time. So that's good enough for us, right? You can take it as big of one. All right. So if you have any other way of solving this one, or better way of explaining this, please let me know. And subscribe to the channel and like the video. And there are appropriate playlists. So this particular video is going to go to this October Lead Coding Challenge. And there are other playlists including backtracking and dynamic programming and general coding interview preparation. And there is an older September Lead Coding Challenge also, right? So, yep. Thank you for watching, and happy coding.